Hello, in this video, we're going to go over some examples of solving both exponential and logarithmic equations. You should have hopefully watched the other videos that were posted for you about some of the logarithm laws and rules, as well as how to convert and change things from logarithmic form into exponential form and vice versa. Okay, here's our first example. We're going to solve the equation 9 to the exponent 2x minus 3 is equal to 27 to the exponent of x plus 3. In this case, it's possible to write this equation so that it has a single power written on each side, the power being the base and the exponent combined, we call the power. So here it's already written as a single power on each side. As well, in this equation, it's possible to rewrite this so that we have the same base on both sides of the equation. So to do that, we know that both 9 and 27 can be written as a power with a base of 3. So on the left-hand side, I can rewrite the base of 9 as 3 squared. So in place of 9, I write 3 squared, and then I still have the exponent of 2x minus 3. And on the right-hand side, I can write 27 as 3 cubed, and then I still have the exponent x plus 3. And using the power of a power rule for exponents that tells us that we multiply these powers, I get 3 to the exponent of 2 times 2x minus 3 is equal to 3 to the exponent of 3 times x plus 3. Now, since the bases are the same on both sides, I know that in order for the expression on the left to equal the expression on the right, the exponents must be equal. So we set the exponents equal to each other and solve the resulting equation. So I expand on both sides to get 4x minus 6 is equal to 3x plus 9. Rearrange so that like terms are combined. So here I'm going to subtract 3x from both sides and add 6 to both sides. And so I get x is equal to 15 is our final answer. You can always check the solution to an equation by substituting it back into the original equation to check to make sure that the left side and the right side are indeed equal. Okay, here's another example of an exponential equation. In this case, it's not possible to write as a single power on each side because of this extra constant value of 5 that we have in the equation. So although there are some bases that are in common, in this case we have two powers with a base of 2, I can't write as a single power on each side. I also don't have an exponent law for adding powers that have the same base. There's an exponent law for multiplying and for dividing powers with the same base, but not for addition. So I need a different strategy here. In this case, what we do is we look for common factors. So on the left-hand side, I have a common factor of 2 to the exponent x. And if I divide both of these terms by 2 to the exponent x, the first term, I have 2 to the x plus 2 divided by 2 to the x. And for the second term, if I take out a common factor of 2 to the x, I have 2 to the x divided by 2 to the x. So I've written this out as kind of an extra step just so we can see what's going on here. So again, here's our common factor of 2 to the x. If this first term is 2 to the x plus 2 divided by 2 to the x, here I'm dividing two powers with the same base, so we know to subtract the exponents. X plus 2 subtract x is simply 2. So I'm left with 2 to the exponent 2. 2 to the x divided by 2 to the x is 1. So what I've done by common factoring is set this up so that I only have one power that has an unknown exponent. Whereas when I started with this equation, I had two separate powers that had an unknown variable in the exponent. Okay, simplifying further, I have 2 to the x times 2 squared plus 1, that's 4 plus 1, or 5. Dividing both sides by 5 gives me 2 to the x is equal to 1. I can now, because I have a single power on each side, I can now rewrite with the same base on each side. So I have 2 to the x is equal to 1 can be written as 2 to the 0. And then because the bases are the same, I can now equate the exponents to get that x is equal to 0. Okay, a third example. In this case, I do have this equation written as a single power on each side, but we don't have an easy way to make or rewrite the bases so that they are the same. So in this case, what we do is we take the common logarithm of both sides of this equation. So when I say common logarithm, I mean a logarithm of base 10. So we're going to take the common logarithm of both sides. And again, that's a base 10 logarithm is a common logarithm. When we use a common logarithm, we don't necessarily have to write that base 10 in there, but you can if you wish. So if I take the logarithm of the left-hand side, I get the log of 6 to the 2k plus 1. And if I take the log of the right-hand side, I get log of 3 to the k plus 2. Now we have a logarithm rule that tells us that we can bring the exponent down in front of the logarithm. So if you recall, if I have log of a to the x, I can rewrite that as, with the exponent multiplied in front, x times log a. So I'm going to use that rule here. So that means that I have 2k plus 1, make sure I put brackets around it, times log 6 if I bring down that exponent on the left. And on the right, I have k plus 2 times log 3. I can now use distributive property to expand on each side. So I have 2k log 6 plus 1 times log 6 is equal to k log 3 plus 2 log 3. I can now combine like terms. So I'm going to rearrange. So I have the k terms on the left-hand side and the constant terms on the right-hand side. So 2k log 6. I'm going to subtract k log 3 from both sides is equal to 2 log 3. And I'm going to subtract log 6 from both sides. I can now common factor the k on the left-hand side. So k times 2 log 6 minus log 3 is equal to 2 log 3 minus log 6. And the purpose of common factoring that k on the left-hand side is now I have k almost isolated. All I have to do is divide both sides by 2 log 6 minus log 3. So then I get k is equal to 2 log 3 minus log 6 divided by 2 log 6 minus log 3. And this is the value of k written in exact form. If you want the approximate value for k, you would type this expression into your calculator. Most calculators will calculate the common logarithm, but not necessarily logarithms using other bases. And then you could round to the appropriate number of decimal places. Okay, here's another example. Here we're going to solve log base x of 2,401 is equal to 7. In this case, we rewrite this equation in its exponential form. So in exponential form, x is the base, 7 is the exponent, and it's equal to 2,401. In order to isolate for x, we take the 7th root of both sides. And again, this is the answer written as an exact value. If you need an approximate value, you would type this value into your calculator and round to an appropriate number of decimal places. And our last example, Here we have the equation log base 5 of 2x plus 1 plus log base 5 of x minus 1 is equal to 1. In this case, we're going to solve this equation by applying logarithm laws. We have a logarithm law that states that the log of any base of, let's say, x plus the log of the same base of y is equal to the log of that same base a of x times y. So this is the product rule for logs. So we're going to use this logarithm law in order to solve this equation. Now, before we get started with solving this equation, we notice here that the unknown value is in the argument of the logarithms. So in other words, the unknown value of x is in the brackets of what we're taking the logarithm of. So there are going to be restrictions on this variable x. So we know that we cannot take the logarithm of 0, and we cannot take the logarithm of a negative number. So we want to make sure that both of these arguments, 2x plus 1 and x minus 1, are both greater than 0. So in order to accomplish that, we need x to be greater than negative a half in the first case, and we need x to be greater than 1 in the second case. So in order to accomplish both of these things, we need that x is greater than 1, because if x is greater than 1, then the first condition is already satisfied. So this is our restriction. We want to pay close attention to the answers that we get for x when we solve this equation. And if there's any answers that don't fit this restriction of x is greater than 1, then we know that those aren't valid solutions for this equation. Okay, so using this logarithm law, so the product law, we can rewrite the left-hand side as a single logarithm. So the logarithm base 5 of the product of 2x plus 1 times x minus 1. And the right-hand side is still 1. So now we have this written as a single logarithm, and we can rewrite this in its exponential form. So we have a base of 5, an exponent of 1 is equal to the value 2x plus 1 times x minus 1. So in other words, 5 is equal to 2x plus 1 times x minus 1. This is a quadratic equation. So in order to solve this quadratic equation, we're going to rewrite so that one side is 0, so subtract 5 from both sides, and expand and simplify. Because right now this equation is no longer in factored form because I've subtracted 5 from both sides. So I need to expand and simplify and collect like terms, and then see if we can factor again, or if not, use quadratic formula. So if I expand and simplify this, I get 2x squared minus 2x plus x minus 1, and the minus 5 on the end here. So that is 2x squared minus x minus 6. And the factored form of this is x minus 2 times 2x plus 3. So in order to solve this quadratic equation in its factored form now, we set each of the factors equal to 0. So we have x minus 2 equals 0, or 2x plus 3 is equal to 0. And that gives me x equals 2, or x is equal to negative 3 over 2. So now we go back and consider these solutions with our restriction that x is greater than 1. And we notice that this second solution does not satisfy that condition that x is greater than 1, but the first solution does. So at the end we say, therefore, x equals 2 is the solution to this equation.